fluctuations in the Gaussian model, basically. So we've done these Gaussian integrations. We've obtained the action. Then from the action, we've put in a fluctuating field. And from that, we've calculated corrections, basically with Gaussian integration. And the singular part of the specific heat correction, okay, so which we derived last time, which I call delta CV. Squared, okay? Remember, there's another piece. There's a mean field part, a Landau theory part. There's a non-singular piece that I just threw away. And so this is the singular piece, and we evaluated it last time, I think at t equals tc, which eliminated this part here. But let's just keep that part in and look a little more generally at this integral in this case. And just remember what all these things are. So I defined the square of the effective interaction range. As big R. And remember that kappa was defined with the interactions Jij. Okay, so we typically make some assumptions on the interactions in the Ising model, especially when we look in the long wavelength or small q limit. That big Q was the dimensionless momenta. So this is a momentum integral, right? So we're integrating over the Brouillon zone. A is a lattice constant. We've been dragging that thing around. When we derive a continuum theory, we're going to eventually drop that. So when we look at a general, sort of a general phenomenological Landau theory, we're not going to worry too much about that lattice constant. And most importantly, the correlation length, again, is basically defined by the two-point correlation function. And that's the thing that's the fundamental object that's diverging at the transition. So let's look, instead of like we did last time at t equals tc, where this part of the denominator disappeared, let's keep that in there and just try to look at the behavior of that integral near d equals 4. And what came out last time was there's something special about d equals 4, and in this case it's called the upper critical dimension. So what we're trying to show here is that basically mean field theory is valid, or these fluctuations which cause the divergence we saw in some cases only occur for d less than 4. So in this case, d, and most cases, d equals 4 is the upper critical dimension. It's not always true. There's other Landau theories that you can derive that have different upper critical dimensions, but like maybe the tricritical Ising is one. I've already rescaled the momentum to give this dimensionless momenta. Let me just do one more rescaling of this fluctuation term. And remember, even though we're looking at the fluctuations of the singular part of the specific heat, other observables basically give similar or the same momentum integral. And so that's really what's important. Okay, so I want to pull out the a over z in the denominator. And then change integration variables again, so that this thing here is just another rescaled momenta that I'm going to call big K, not to be confused with that kappa, which I've been writing up, big kappa, which I've been writing up there. It shouldn't be confusing because I don't use kappa anywhere. So big K, it's Q Z over A. So the thing that we're going to analyze is simply we have an integral. We have to change the limits of integration. Okay, so originally they went from minus pi by a to pi by a because we have a periodic system, and that's the first Brouillon zone. That's all we have to consider. We rescaled it, so it's just pi, minus pi to pi. So now we're rescaling it again, so it's minus pi d over a, pi d over a. K is our momentum. Okay, so it's similar to what we did last time, except we've kept in, well, so the integral is just more complicated. And keep track of the prefactor, because the prefactor has a divergence in it. So there can be a singularity in either of those, either the prefactor or this piece. So you have to be careful about that. And just like before, that's going to depend on dimension, because as you know, to analyze this type of integral now, which is in higher dimensional space, we basically do it in spherical polar coordinates in d dimensions. Okay, so let's rewrite this integral. Let's just look at the integral part. The prefactor just has this simple dimension dependence. You see the upper critical dimension playing some role there already, right? Okay, so we imagine we have some sort of K-space. Interactions are cutting off our integral in some way, which isn't quite obvious. Then we have some sphere maybe in this higher dimensional momentum space. And so we define a surface area to that sphere in higher space, which I wrote last time, just SD, KD minus 1, dk. So now K is like the radius of that integral. And so the limits of integration are then replaced because we're integrating over like the radius of that sphere, right? So they go from 0 to some radius, which is, you know, related to this cutoff in some sense, but it could have prefactors or scaling or something like that. So we'll just imagine that we're near the critical temperature. So the correlation length is large enough that this upper cutoff just somehow scales like that. So the integral is I'll say 0 to, I'll call it K naught, so we don't have to think about it too much. So for general dimensions, you can just evaluate that integral in the case where, say, this is tending to infinity. So where this upper limit tends to, so in the limit where this goes to infinity, then this is just the product of gamma functions. D minus 2 minus d over 2. Okay, so the dimension occurs in the gamma function. This one could be negative. The second one can be negative if your dimension's high enough. What's a gamma function of a negative argument? No, I don't know. It's singular. It doesn't make any sense. If you write it out in terms of the definition, it's singular. So the integral only works, you know, it gives a simple number only for the case where these gamma functions aren't singular. Then it's something finite, you know. In the case where you approach TC, this thing's finite, and the divergences come from the prefactor. That's the point. If this is 4, then it's gamma of 0, which is also singular, -1, -2. And then when it doesn't blow up, when the arguments of the gamma are positive, definite, or positive integers, then it's just some number. Who cares what they are, right? It's just some prefactor that you can essentially ignore. So in the case when d is less than 4, then the singular part of the fluctuation correction to the specific heat is dominated by this part of the prefactor here, the divergence of the correlation length. And we can use this to define an exponent if you want. Again, this is conceptually problematic because the mean field part only has a discontinuity. It doesn't have any sort of divergence like this. But if we wanted to ascribe an alpha due to this fluctuation, then we could. And you'll see it written like this in the books. Correlation length, right there. Square root, kappa 2t minus tc. So if you put that in to this expression, this will just give you a definition of alpha. Where alpha is 4 minus d over 2. And it's again a new divergence just from the fluctuation term. I don't know why you want to define an alpha in this case, but you'll see this written. Okay, so in that case, d less than 4, that prefactor matters. What I didn't do d equals 4 last time, because the integral, it's a special case. So, and d equals 4, this prefactor disappears, right? So now, any divergence or singularities are arising from that integral. So that's kind of a special case. And let me write the integral. So it's k 3 dk. Okay, so we're not going to solve this thing exactly like we did in any meaningful case, but we can note that this integral has behavior at each of its limits. So the contribution from this, if you take the limit when the argument is near 0, so the limit when k goes to 0 of the integrand is 0. So the contributions near that lower limit of integration don't give you much. Everything comes from the upper part. So the integrand goes at 0, so it doesn't contribute. So any divergences come from the upper limit. As long as we're sufficiently close to the critical point, right? Doesn't contribute for t goes to tc, say. So then you can approximate this integral. There's some point where the lower limit does start to contribute. Maybe it's epsilon away from the upper limit. Doesn't matter. K naught will be something that behaves like correlation length over A, say. And for large enough k, we can just write the denominator as k to the power 4. So we get k3 over k4. And then from the upper limit, being proportional to the correlation length, gives us something like 1 over k, so it's a log. Correlation length is like 1 over square root t minus tc. So it's minus 1/2. So when you hear people say that there's a logarithmic divergence right at the upper critical dimension, it just comes from the upper limit of that momentum integral. Okay, it's just a special case. So let's look at d greater than 4. For d greater than 4. Right, so now there's no issue with this because it's like 1 over the correlation length. So the prefactor doesn't diverge, but let's look at the integral. And just like this case, the singularities will arise from the upper limit of the K integral. So let's just look at that upper limit. Well, again, if I replace this with some epsilon, that's not that far from K naught. Then the part of the integral that contributes is when this is large. So this thing's pretty close to K to the D minus 1 over K to the 4. And write it like this. Depending on this relationship between epsilon and K naught, it's just sort of a finite difference, but say you're very close to T equals TC. This piece is still going like this, Z over A, correlation length over A. This time it's to the D minus 4 in that limit. So we have correlation length over lattice spacing, D minus 4. That part that didn't diverge is this part, 4 minus D. So the integral gives you the same, or gives you the opposite behavior, and it cancels the prefactor in that case. This is the same behavior as we saw last time right at TC. I mean, in some sense, this is very similar. We're just being a bit more careful. So specific heat doesn't diverge, and the mean field term with that discontinuity dominates. Okay, so again, the moral is that since the fluctuations give new divergences for D less than 4, then we conclude that mean field theory plus Gaussian fluctuations isn't reliable. It's only reliable in this case. And this is actually proven rigorously. We're not doing it here. That the critical exponents take mean field values for D greater than 4. Okay, so we've just done a perturbation type theory, expanding into fluctuations, doing the Gaussian integration. But if you're more careful, you can prove that the critical, this is what I said in the first day of class, that the 4-dimensional critical exponents. So this is the example for just for the specific heat. I like this one because there is no divergence And so you can, you could ask if there was a divergence in the first term, and then you're getting additional divergences. You'd have to try to compare these things. But in this case, we don't have to, because in the mean field case, there's just this discontinuity, right? And so now we're just adding small fluctuations to this. And if we see a divergence, it's much more obvious. So again, d equals 4 is the upper critical dimension, like I wrote over there. Above which the theory is self-consistent. Oh man, self-consistent. To be self-consistent below d equals 4, then we have to have a case like this where at TC, delta CV would be, say, small, less than 1. So we can ask if there's any criterion for that to be true. Let's call it this CV. We'll just say that thing should be small. It shouldn't have this built-in divergence. So how do we ensure that? Okay, so if you look back, you have a prefactor A. Oh, did I forget my 4 here? How long was that? Make a note of that. So we have delta CV. I left it out there, but we would have, let's say, A over R4. And then I'm going to write that piece as reduced temperature to the minus alpha. The integral is finite. It's all those gamma functions up top here. And then we just have things like 2D in front. So this is all we require. So this thing has to be less than 1. Or putting in that value for alpha. So it's t to the d minus 2. Has to be less than. Okay, so there's a condition to be self-consistent. It's that the reduced temperature, raised to this power, has to be much less than basically this effective interaction range, or the ratio of that effective interaction range over the lattice spacing, okay? So you can say, well, maybe there's some systems where, this thing is large enough that this condition is satisfied. And actually, one case, it's a case where R is infinite. Remember we solved the case for infinite range interactions? So when R is infinite, then this thing never catches up to it, even if t goes to 0. But if R is not infinite, then there's always going to be a region close enough to the critical point where this divergence wins. Okay, so that gives another, we solved the infinite interacting case, showed that the mean field critical exponents, like the Landau theory, was the exact theory in some sense. So here we're seeing it again, and we're seeing it come out in this condition. But if R is not infinite, then there's always some region near criticality where this theory breaks down. This is called the Ginzburg criterion. It tells you sort of, it even tells you experimentally, like if you know somehow something about the microscopic interactions, it basically tells you how close you can get to the critical point before fluctuations start to matter. So it explains the form of sort of divergences that have been seen in some experiments in the past, But for us, it's more valuable as a way of understanding when mean field theory is valid. For finite R, the criterion or the condition always breaks down. Or T sufficiently close or D less than 4. And this breakdown, again, is due to, I guess, long distance properties. Or, divergence of, say, the correlation length. So in order to understand how to correct the theory, we should be focusing on long distance properties. And so one framework for doing that is to develop a long wavelength sort of a phenomenological theory. So let's So remember we did, you've developed a Landau theory. I mean, this is sort of a microscopic theory in some sense, right? Because we have A's in here still. We have your lattice, whatever crystal lattice you're looking at, that really defines sort of the short distance cutoff or the UV cutoff in the field theory sense. But it's very straightforward to go from, this microscopic picture to the phenomenological Landau theory. So you've constructed a Landau theory just with symmetries, right? The symmetries of the order parameter. And you've argued that phenomenological theory captures all the properties of this, if you will, microscopic theory. So we can make that more concrete by just showing the correspondence directly. So let's look at the phenomenological form of the Landau theory and just connect it to this very quickly before we move on. And this will derive the phi-4 theory that you can write down phenomenologically, but this will derive the phi-4 theory and show that that's really the long wavelength physics that we're interested in when we talk about properties like this. So let me just take a few minutes and look again at that. Phenomenological. And I want to remove all the details like A that are occurring in here, okay? Okay, so first off, if we're interested in, the long distance behavior and the correlation length is diverging, then we should be able to eliminate A and only focus on sort of the momentum expansion of the interaction that we've written before. So half of this, I've basically done this all before. In some sense, I'm just bringing everything together. Because after today, we're done with this and we're moving on to the renormalization group. So let's just look at how we pull out the phenomenological theory from this. All that information about the lattice interactions shouldn't contribute somehow near the critical point. We only need the information. Remember in the Fourier transform of the interactions, and assuming it varies slowly on the scale of A, then as we wrote before, we get that Q squared form. So remember, that was important when we calculated the 2-point correlation function. So we have an action. You can look back, I'm not going to write it down. We should be able to approximate that action by doing a Taylor expansion of the log hyperbolic cosine piece. Which is assuming that basically the expectation value of that argument is small. Okay, so this gives us, forgetting this constant, which doesn't matter, look back in your notes for the form of S, if you need to. Okay, so we see what's going on here. We're getting the 5-4 theory. We have fields. Okay, so I have a term that depends on the interaction. I just want to make sure I only worry about the long, or the small q piece of that. Then I have a piece that looks like phi squared, and I have a piece that looks like phi to the 4. Okay, and they have some prefactors in front of them that you get from this expansion. So let's go to Fourier space and solve these solve for each one of these terms. Then I can use, for example, J of Q and so on to simplify this expression. And we'll relate the parameters in that expansion to the phenomenological terms in the Landau theory that you would build by symmetry, if you were to do so. Okay, so first let's look at the quadratic term. So I have Jij, it's the inverse matrix elements. I also have a phi squared. So they're both quadratic in principle, but I have two different fields here, and I only have one field there. I can write them together using a delta function. I'll call it S naught. Phi I, T, inverse interaction matrix. The thing we don't want any details of, basically phi j. Okay, so we're going to take the Fourier transform. Remember how it works, the fields. We do the fields, we do the interaction. That's the Fourier transformed interaction over there. Let me just sketch out one important part. I'm not going to do all your Fourier transforms for you anymore. But just let me make a note of what's important here. Okay, let me just write it in a different color. Okay, so when I have this case where I have like two fields, okay, when I have a case that's like the second term, when I have a sum over two fields that are the same, so let me call it this. When I put in the formula for the transform fields, so remember it's 1 over n. Okay, so I'll do it. So there's two of them, 1 over n squared. There's two fields. So let's be careful and use two momenta in the Fourier transform. Okay, that's the Fourier transform function, if you will, or the Fourier transform field. So I need a q and a q prime there. And I can write it like this, e to the I r. That's the position vector of site I dot, and I'll write it q plus q prime. So we can use a delta function here, but the fields, you know, in the delta function, you have, say, a q minus q prime. So I wrote it like that. Okay, I could have used k or something there, but I have a sum or integral over I. I have two different momenta. If I can write it like that, then I have a delta function. So what it means is I have to constrain, say, q prime to be minus q. In that case, and I would get something that's like giving me one contribution, but I have q and a minus q. Okay, so that's pretty standard, but it's worth seeing once. So that dictates how that quadratic term looks in momentum space. So then, okay, so that quadratic part in the white, I'll check it all in terms of details, but I write it like this, T over J of Q. We Fourier transform that thing too, and phi Q. Okay, so now this thing can be expanded. We know what we want. We want this thing here. See, I can JQ. I have a kappa there, so I can write this in terms of R. One minus it'll look like this. 1 over 2d r squared q squared. Sure, why not? Okay, so let me look at this piece inside the square brackets. Just expanding this out. Okay, like that. So near t equals, let's see, the critical point, I'll replace j with, what do we want to do here? Okay, so this could be t over tc. It's an additive. This is t over t. C, it's just multiplicative on this. So somehow I'm assuming that we're going towards 0, we're approaching the critical point. I can just fudge this a bit and write t over tc minus 1 plus 1 over 2d r squared q squared, or reduced temperature. Okay, that's what I really care about. The phenomenological parameter needs to have that reduced temperature in it somehow. So then 1 GDQ d squared, that's right, yeah. Did I forget a 1 somewhere? No, that's right, yeah. Okay, so now I can put that into my S naught. That'll give me the quadratic piece. Okay, I have 2 fields. So I'm trying to develop a phenomenological theory here. So I'm just going to start rescaling variables to suck in all the parts that I don't want. And all we're going to do is keep basically the signs of terms in front of the, say, quadratic and quartic pieces. And yeah, so including the behavior on the dependence on the reduced temperature. Because in the Landau theory, remember the coefficient of the phi squared term has to change sign at t goes to 0, right? So let's just redefine variables. I'll call it tilde. It's a new field. Which lets me rewrite the action in terms of phi tilde. Okay, so I have a piece here plus a q squared, and that's the piece that I'm going to call just some parameter r. It changes sign with t. Okay, so call this piece and I don't care about the tildes. I don't care about anything. Let's just rewrite S naught. Let's say phi tilde, drop the tilde. So I have the Q space form for this. Let me write it in the continuum. Okay, let me write this down and then I'll explain just a little bit about the continuum. I think we already know, we've already done this once. So if I take that sum to an integral, it'll look like this. And I have r plus q squared by q. And I've used there the fact that, let's see, how does it work for, so remember I have a unit volume, sum over Q, and I need a fixed volume when I go to the continuum limit, but I need that unit volume to go to 0, so it looks like this. Okay, or else 1 over V, sum over Q, goes to 1 over 2 pi d integral. And volume is L to the D, so it's N times A to the D, right? It's this thing here. That's your volume. That's L to the D. Okay, so we've done that part before. Now I have my quadratic piece. If you've done any field theory, you've seen this before. I have a quadratic piece in momentum space. I want to just transform that back into real space, and that'll give me my quadratic theory, the thing I'm looking for. So you basically just diagonalize this thing in momentum space. That's what you've done here. So let me, before I transform it back, let me just give you the answer. Then just say a couple details about this Fourier transform. I want X or R here. I'm not ready to make this decision. I'm going with X. Oh yeah, that's a good decision because I have a small r there. That's a gradient. Let me explain this. So, okay, it's good for your nodes. You see every step. Take the continuum limit. Okay, so I just redefine variables, taking the continuum limit, and I'm going to Fourier transform it back. I get a grad phi here. So let's just talk about where that comes from for a minute. I'm going to come back to so what I've done is these two pieces, right? I'm going to come back to this piece because it's straightforward. But I think it's worth mentioning the relationship between this and what's the Q squared piece in momentum space. So let me grab a different chalk and say something about that. I mean, it looks like it makes sense when you see it on the chalkboard, and then when you go to do your assignment, I know what it's like.
Why not be squared? Squared.
Yeah. Yep. Thanks. As you know from symmetry, there's no magnetic field. You need to have phi squared. Okay, so remember that when you define the lattice sum, when you find the continuum limit from the lattice sum, you have that unit volume, which is tending to 0, which is keeping the total volume of the integral equal to the total volume of the thing you're summing over. So once you define that convention, everything in terms of the continuum, including the continuum Fourier transforms, falls out of that. Okay. So that's a momentum space case. I mean, most importantly, L to the D, which is defined as your volume, it's a number of points. And in real space, it's n times a to the d. So a to the d is a volume per lattice site. So that's your unit volume in real space. So a to the d times any sum is a thing that goes to d dx. And when you have something that's like 1 over n, then obviously this goes to a to the d, L to the d. That gives you 1 over volume of the integral. Okay, so things like, whenever you take the Fourier transform, you need things that are like delta functions, like just what we used right here. So if you take that definition of the Kronecker delta, and you apply this in the continuum, then for example, X's are R's. You get something like, okay, so you just replace with that formula there. So that implies if you have dd, if you have the integral over x e to the minus Q minus Q prime. That's just V delta Q Q prime. Straight from that formula. But in the continuum limit, we can change the Kronecker delta to the Dirac delta. You have to be a little bit careful with that. And essentially, you just look at how the, in the case of infinite volume, how the correspondence between volume and sum and integration goes. So let's say, I think when V goes to infinity, this will give you Q minus Q. So if you want details about all this stuff, look in Goldenfeld. I think is probably the best. Okay, so I can take my definition of the Dirac delta function in terms of the continuum variables, like this. The only other thing we need for that, to do that Fourier transform, is the Fourier transform of the fields. And you can do the same thing, change the integrals to, or change the sums to integrals. I think the only subtlety there is what you do with A. Because you have to be a little bit careful about how A goes to 0. You can set A as a unit vector and take the other limit, but what we need is, say, phi I. This is something we would do on the lattice. I think I already wrote this. I Q dot, I'll call it X now. Apply these formula and look to see that you get, in the continuum, something like that. And similarly for the momentum, for the inverse. So if you have phi of, let's call it phi of Q. Here's my space integral, e to the minus I Q dot X. What did I forget? Phi of X. So again, you just, because of this normalization, because of the way you take the continuum, like the normalization of the delta function, if you will, you get your 2 pi over d here, okay, but not here. There's other ways of defining that normalization, but it doesn't matter. So how do you get this grad term? Let me just do it backwards in one dimension. So I have an integral, so let me set d equals 1. And just use these formula. So my integral is integral over dx. And I just have one dimension. So what I can do is take the derivative of the Fourier transform, right? I'm in X space here. So I have dx. I have two of these things. I'll just write it like this. I have the Fourier transform, so I need 1 over 2 pi, raised to the power d equals 1, dq, phi of q, one dimension, e to the I qx. This whole thing's squared. Let me take that derivative. So I got I coming out of that from the exponential. I have a q, but I got to leave that in the integral. So dq phi q dI qx. I've written it as a square, but I should really write that it's two Fourier transforms with different momenta. You want to be very careful. And then we can use the definition of the delta function. Okay, so this might be too much detail, but just in case you haven't seen this before or something. I have two i's, give me -1. I have two 2π's. Okay, so I have my integral over x. I have e to the iq and q prime. Okay, so that's the relationship between q and q prime. So I'm going to get that q is minus q prime out. And I need the delta function. So I'm going to use in the continuum the Dirac delta function. Right, so I just use this expression here. And my d equals 1, so I can get rid of one of the 2π's. So I'll get something like -1, 2π, dq by q, minus q, q, phi, minus q. The minus sign doesn't matter out front. I mean, it just matters that it's not imaginary. But I can change that minus sign. I can just take q to minus q. Everything here looks the same, and I just get rid of that minus sign. So that is like the q squared piece right there. Right? And I just have the d-dimensional integral instead of the one-dimensional integral. Okay, and this part here is like the thing I started with. I just did this proof backwards up there. Okay, does that make sense? Any questions on that? So this is your quadratic term. Let me just look at the quartic term really quick. Okay, we have a phi squared theory, if you will. How does this turn into a phi 4 theory? Well, I guess I just erased it. No, I left it. So now we want to look at this piece. We could look at all the higher order pieces. This tells you what's allowed in the Landau theory, in some sense. We haven't thought of the symmetries or anything. We're just plugging these in. So let's go on to the quartic piece. It's similar. I'm not going to do all the steps. It's easier. You don't have to deal with this grad phi piece. Call it S1. Why not? What is it? 1 over 1/12. I'm going to pull out that t to the 4. Okay, let me use the same. I'm going to use this here. Just write it in the continuum limit. And And then I'm going to rescale this piece out in front. Whatever, call it tilde again. I'm not going to show all the steps, because there's only one thing that matters about the prefactor to that sign. And you know from when you construct these things phenomenologically what that is. It's the sign of that term, right? So my S1 oh, I'd have to sum in that step, but let me pull that out with a integral. Phi tilde 4. That's a continuum field now. Drop those things. Who cares how the field has been rescaled? And let me define that prefactor as, I'll call it U. And the only thing I cared about was that this thing's positive. And there's, as far as I can tell, no way for that thing not to be positive. Why do we care? Why do you need that term to be positive? Yeah, it bounds the, keeps the free energy looking like this. Even if that R term changes sign, it keeps everything bounded. So it's a stability condition on basically constructing a field theory. So then the phenomenological action is just what you expect. So I have a grad term in here. That's your continuum phi 4 theory, or your Landau, Ginzburg, Wilson theory. Okay, we've basically been derived from microscopics, and all we've done is change absorb all of these microscopic parameters into what you would recognize as your phenomenological parameters. Questions on that? Your mean field theory corresponds to, phi is the saddle point approximation and so on. Okay, so this is still a full interacting theory in some sense. And we can take approximations, take out approximations to solve that. Here. Ignore all fluctuations in space in your field theory, and you get the mean field theory. Then you just minimize this thing. I think you've done this many times. Which gives your mean field solution. Okay, so that's just your reduced temperature and so on. So that object contains essentially all the physics that we care about in this long distance limit. I want to do a quick and sketchy dimensional analysis on this thing. So I have these R's and U's, phi's, phi 4's. I mean, this thing's been derived microscopically in some sense, so we know everything's there. Let me identify the dimensions of every piece of that action. Goldenfeld does this. It's just a couple pages in Goldenfeld, but I think it's nice because it shows that what I want to show is this idea of upper critical dimensions and so on fall out of the action and not just out of some observable like the specific heat. So we can see the problem and the breakdown, if you will, of Landau theory just from doing dimensional analysis on that action. So as I identify the dimensions of the various quantities. Most importantly, this thing is dimensionless. Remember, it occurs in the functional integral. Like that. So each one of those three terms, 1, 2, 3, in that action, must have dimension 1. If you want to call it that. So first, what's the first one? Integral. So I've dropped the vectors on that x. So that thing's dimensionless. So I'm going to use a notation like, say, I forget what Goldenfeld uses. You could say the dimension of, say, the integration variable. I'll use a length, L to the D. Right? I'm just saying there's a length that's being defined, and the dimension of this part, say, is L to the D. Actually, I'm not sure. Let's just use this notation. Let's forget that dim. I forget which one Goldenfeld uses. Okay, so that first term, let's just look at the dimensions of everything. So I have the integration variable, so I'll just write it. So the dimension is L to the D. I have two derivatives of the field, which will give me L to the minus 2. But then I don't know the dimension of the field. So that's what I'm trying to figure out. That's the whole thing has to be unity because every single term has to be dimensionless. So from that, I just know that the dimension of the field. Wait, do I need a square on that? Yeah, it's two derivatives of that field squared, if you will, in terms of the dimension. So I should get something like 1 minus d over 2. So now I know the dimension of the field. That second term, which is r over 2. So we need to know, 2 doesn't matter, but we need to know the dimension of r. So I have L to the d from the integration variable. The dimension of r I don't know. And I have phi squared, which is L to the 2 minus d then. So that implies the dimension of this thing r is inverse length squared. So we can define our length scale in terms of that, if you will. And the third term, the phi 4 term, so u is the thing we got to worry about. But now we see how it works. Let's do the same thing. We get the dimension of u, d minus 4. So we can rewrite s in terms of dimensionless variables. So all the fields and coordinates, I'll write them as tildes. I'm just scaling away these dimensions. And let me define a length scale independent of the dimension. So that relates R and L. Like that, if you will. Right? So then in these transform coordinates, or dimensionless units, I've gotten rid of the L's, I'm replacing them with R's. D minus 2 over 2, right? R4 U tilde. Yep, U tilde. Phi tilde to the 4. Okay. You can do this. So the last one that matters are d over 2 over 4 U tilde, right? And so once you do this, and you pull through this r to the minus d over 2, you get your phi 4 theory back. In terms of these fields, I've taken away r there, so all I have left is u phi tilde to the 4. And the Gaussian, like I said, this is your interacting piece. The Gaussian approximation is when this piece is 0, and then you can solve the Gaussian integral, right? But look at u, there it is, u over 4. If you write in terms of r, that u tilde over 4, r to the d minus 4 over 2, which is u to the reduced temperature, because there's no escaping that. That's the thing that changes sign, right? This somehow is the parameter that we're expanding under. When we do, so we do a Gaussian theory, and then we have this piece, the phi 4 piece, and we're doing a sort of perturbation or a fluctuation expansion in the Gaussian theory. That's really the parameter that we're expanding under. u to the t d minus 4 over 2. But, you know, there's some dimensional dependence here, and again, you see the upper critical dimension follow to that. So for d greater than 4, so the perturbation theory in what u tilde works, but for d less than 4, g diverges. So Gaussian plus fluctuations gives the wrong result. So, in other words, you could write, as we'll do from time to time, especially if you take maybe 733, we will study perturbation expansions, and basically that's what you were doing when you looked at this specific heat. You're imagining that you have a partition function, right? That's the functional integral over these dimensionless fields, something like h naught plus h1. That's your phi-4 term. Interactions. So what we're imagining doing is, you know, writing this as d phi, and then Taylor expanding 1 plus, maybe it's minus, I don't know, h1 plus 1/2 h1 squared plus blah, blah, blah. But the expansion parameter is g. Okay, so that was quick, but again, it's in Goldenfeld if you want to see the not quick and dirty explanation. But the point is, you know, even though we've looked at the specific heat fluctuation, you don't need to look at the specific heat fluctuation. So, you know, everything we did last week, you could have just not done, and we would have been way farther along in this course. But, you know, the point is, if you define this action, you do a dimensional analysis on it, and you rewrite it in terms of these dimensionless variables, then G is a thing that we're trying to do the expansion around, and the dimension matters. So it's just another way of seeing the upper critical dimension. So this is all the possible ways that I could explain the upper critical dimension, I think, in this class. So I'm completely exhausted in explanation. So I think, again, we brought it back to what I said the first day or two. We've talked about the idea of Landau theory. You know, we've derived continuum theories. We've looked at, you know, microscopic theories. We've shown how they correspond. We've looked at different exponents, how fluctuations basically don't work as a perturbative expansion for d less than 4. And so starting next class, what we're going to do is start thinking of this idea of the correlation length and how the correlation length is diverging. I don't know what I just pointed at there. And from that, we'll start deriving basically the renormalization group. We'll do real space RG, and then we'll do a momentum shell RG that's going to calculate eventually corrections to the critical exponents in the correct way. Okay. So that's a few more weeks of class down the road. So. Okay, so we'll start into the RG. We'll talk about scale invariance at the start of next class on Friday. And see you guys then.